So the first thing I need to say is that as much as this talk has been billed as coming from Strathclyde, or as forever will now be known, the Impossible University, this is actually something that's involved a huge long list of partners from all across Mission Atlantic. And I do need to start by saying thank you to all of those that have enabled this work to happen. So thanks to Yuri and the PML team for sending us the terabytes of universum output that have allowed us to build these Strathclyde 2E models. Thanks to all the case study partners, you've all been great in providing us that important local knowledge we require to build the models. And I think perhaps the most important one really is to all of the mobility fellows that we've had come from the case studies and visit us at Strathclyde, because you've taken real ownership on those models and done a fantastic job of building them yourselves. I'm very impressed with the fact that so many of you guys were master's students and PhD students. You've really been able to knock it out of the park. So in terms of the science, I'm here to now talk to you all about sort of management strategy possibilities and what those might be, given that climate change is threatening fisheries and food webs across the Atlantic Ocean. And I think it's important to remember that when it comes to matters of strategy, it's as much about actively deciding what we won't be doing or what's not important as it is about trying to decide the sorts of things that we want to prioritize and want to achieve with those management strategies. So when we have a poor management strategy, our objectives are going to be in conflict, and that's going to undermine successful outcomes. We've heard plenty of that over the last day or so, with Anna's talk as well. If you sit there and think about the conflicts between fishers, between offshore renewable energy projects, or between conservation targets, it's impossible for us to sit there and just hope that we will end up with the best outcome from all of these independently. If we sit there and try to manage things like that and just hope for the best from each, then we're guilty of what we say in English is cherry picking. So this is that idea that you might have punnets of fruit on the shelf, and rather than just taking what's being sold, you try to take the best cherries from each and make some sort of bulk offer that was never really possible to achieve. Okay, so we need to have a collection of options in front of us that we can assess and decide which one of these is desirable in order to make some sort of sensible choices going forward. So to kind of run with this analogy a bit further, we can lean on a little bit of economics, and we can try to create a space of management possibilities on the basis of the different objectives that we're valuing. So here we have a choice between a collection of cherries. We have size increasing on the x-axis, and we've got the color of those cherries changing on the y-axis. And we want to get the biggest and reddest cherries because that's what makes everybody happy. Just deciding that's priority. It does not make any sense for us to take something that's on the inside of this cloud of management strategy possibilities. Okay, this is a suboptimal point because for no cost in color, I can get a bigger cherry, and for no cost in size, I can get a redder cherry. Sometimes we're lucky and things are actually independent from each other, and it's the case that the biggest reddest cherry does really exist up there in that top right corner, and so we didn't need to worry choosing strategies where there's some sort of conflict going on. We'll notice that's the case when on these sorts of biplots we see a change of things, so this right angle shape. This is referred to as the Pareto front. If we have that right angle, things are possible to manage independently. Okay, so all is happy, there's no conflict in the system, we can just carry on choosing our silos. But that biggest reddest cherry is not always available, and sometimes we're going to be forced into a trade-off. Here we can decide to have some very nice red cherries or some big cherries, and there's a sliding scale between those two states, which we now get to have lots of lovely arguments over and fight, trying to find that perfect sweet spot, especially given different stakeholder views. It might be even worse, and rather than having a continuous trade-off, we've actually just simply got two choices here, two mutually exclusive options. You can have a red cherry or a big cherry, and that's it. I'll say it's worse because the choices are fewer. However, in some ways, there's not really much of an argument here. You just got to pick between two binary options, so that can actually kind of help focus on decision-making and make things a bit simpler. But I've spent the first 4 minutes of the talk just talking about cherries, and we're not here interested about fruit. It's an integrated ecosystem assessment symposium. We're largely a marine crowd. So we're instead thinking about management choices and management strategy possibilities in terms of ecological issues, in terms of livelihoods, health, and potential futures that are available to the next generations. So we want to know what's coming for the Atlantic, what are the possibilities in front of us. And to support that, we've gone and created a collection of Strathclyde 2E end-to-end ecosystem models throughout the course of the project. So again, big shout out to everybody that's been involved in this. For this particular study, we're using 9 modeled regions. So that's 7 case studies with a couple of the oceanic islands bumping up the number, and our original North Sea model as well up there at the top. And within each of these 9 modelled regions, we have subjected things to a set of climate change conditions, all forced by the numerism runs that Yuri provided. So we have a factorial cross of 2 time periods showing half a century of climate change, 2 shared socioeconomic pathways reflecting different potential scenarios for changes in climate, and also 2 different forcing system models for numerism, which allows us to reflect some of the structural uncertainty in our climate projections. So the factorial cross here provides us with 8 climate conditions for our 9 different regions, and we've decided within those different climate conditions to nest a Sobol sensitivity analysis of fishing practices. So this is going to generate a huge set of potential management strategy options. This particular fishing design includes the 10 different harvestable guilds within Strathclyde 2E, and these are ranging from the benthos and the macroalgae through the fish and to top predators as well, because some people decide to harvest these, sometimes these are bycatch. We have 1,000 Sobol samples, that's 1,000 different strategies sampled across these 10 exploitable guilds. And the 12 Sobol sets allows us to look at the interactions between the harvesting of all of these different fisheries, because it's not the case that you can harvest those different fisheries independently if they're connected in a food web of who is eating whom. So in total, this is creating an experimental design which requires 864,000 Strathclyde 2E model evaluations, which we're rolling through on the machine back in Strathclyde and taking just over a month to get the steady state outcomes for all of those. They are not all ready yet. Some of the regions are still being processed, but I have 5 of the regions to show you all today. If I put that 500,000 simulations on the screen, first thing I kind of want you to see is that the regions are grouping out quite nicely on our principal component analysis. This ordination has been generated by comparing all of the different biomasses across the different components of the food web. So this is sort of the state of the ecosystem summarized down to 2 dimensions. And you can see that there's that clear clustering on the basis of region. So despite the variation in fishing practice and despite the change in climate over half a century, it is not the case that Norway is going to suddenly start looking at the Celtic Sea. Okay, there will be change, but it's not enough to cause that kind of drastic reorganization of things in the Atlantic. A little bit of overlap in Senegal and a little bit of overlap with our oceanic islands on the bottom left. That first principal component is explaining about 40% of the variation across our simulation set and shows the difference between lower and higher production. Our second primary component is explaining a further 20%, and that's expressing the difference between the biomass being concentrated at the plankton and the fish end of the food web versus towards the top predators. Ideally, we'd have a third principal component as well to absorb a bit more of the variation, but that starts to make things complicated on the slide, so that can wait for the paper rather than being the thing to see today. What's interesting is to be able to start seeing how much of this variation we can explain in terms of other aspects of climate. So here we can get a bit of a sense of where the regions are, but if we now start to cluster things on the basis of whether they're the simulations from the 2010s or the future in 2060, we can see a consistent pattern of shifting from those black holes to the left into the white holes. They are overlapping, so we are able to manage things and just kind of maintain some sort of state in the middle in the overlap zone. But for the most part, what we're seeing is the effect of climate is to reduce production in all of these systems across the Atlantic. If we look at the shared socioeconomic pathways, there's not particularly much going on here. And that's simply to say that over the course of the next 50 years, we've already locked in quite a lot of the climate change signal of emissions that have already been released. Okay. Finally, there is some influence from the Earth system models, but this is not consistent about which Earth system model is doing what for which region. So as an example, looking up the Norwegian shelf, we can see that the green hull is wider than the grey. So that's saying a larger range in primary production for this GFDL forced simulations. But down here for Senegal, it's the opposite. It's CNRM that has wider production. So some of that structural uncertainty is represented, but it's not something that's giving us a consistent pattern to be worried about. So having had a bit of a look at the impacts of climate on this set of simulations, let's now start having a little bit of a think about the fishing. I will walk your way through the graph and say what's happening, but the main message is that there are lines, the lines are red, and red is bad. So we're seeing climate change driving down maximum sustainable yields across the different regions, and this is going to be linked to that change in primary production. It's the case here I'm showing you the planktivorous fish, the top 2 rows, and demersal fish, the bottom 2 rows. We have these outputs for all 10 guilds, but it becomes a bit too much. You'll see that all of the regions are showing this reduction, with Senegal somehow faring a bit better under climate change. That'll be interesting to dig into the simulations to see what's forcing that in terms of the drivers. The SSPs are contained within blocks. These don't change too much between each other, as you saw already on the climate change simulation. And again, CNRM and GFDL are in different rows. Again, sort of similar trends across the board. So even with this uncertainty in our climate projections, this message that climate change is going to be undermining fisheries is consistent. And some of these drops are quite large, 25 to 50%, or up to 75% for some of the simulations. Now, it's worth saying that this is a global maximum sustainable yield. It's not just one point on the yield curve. And that's because all of these different fisheries are interacting with each other. So it is not necessarily the case that you're going to be able to achieve this maximum sustainable yield for all of the different gills simultaneously. That's bringing us back to our cherries, and we need to start deciding what are we going to do under the interactions between these different fisheries in the system. Now, it would be possible to look at all the pairwise interaction surfaces that are coming out from the simulation set, but we'll be here for a very long time looking at lots of different combinations of 10 different fisheries. So instead, we can take a more holistic view and look at the ecosystem scale of what's going on. In here, I'm sort of starting to plant the seeds of the idea that we can look at the trade-off between the food web and sort of the ecosystem aspects of the system and what the fishing outcomes are going to be from the system. The two metrics that we're going to use and talk about in the next couple of slides are human appropriated net primary production for the fishing, as this is going to provide us with a common metric through which we're going to be somehow able to say this is how much landing a whale is worth versus landing plankton versus cod. It just doesn't make sense to do it on the basis of weight. You could try price, but there's different markets, so human appropriated net primary production is the metric we will use. On the x-axis, to get a sense of what's happening at the food web, again, rather than doing all the biomasses, which you've already seen through the principal component analysis, we're going to look at mean trophic level, because that gives us a sense of how the ecosystem as a whole is behaving. So now what we have are our Pareto fronts for each of the different regions on these two particular metrics. What I'd like you to see is that we have a shift in that Pareto front as a result of climate change. So the black line is the present day, the red line is the future climate change scenario, and you can see that consistently climate change is pulling the maximum human appropriated net primary production down. So we're going to be able to take less from the sea as a result of climate change. That's in keeping with the maximum sustainable yield figure. The second thing I'd like you to spot are these little dots at the bottom of each of the clouds. Those are reference points. Those are the unexploited system that Strathclyde 2E is simulated, and they're also coloured. So we have the black dot showing present day what would happen if we didn't exploit the system at all, and the red dot being the future. And for all of those, there's been a shift to the left. So that's telling us that in the absence of fishing practice, climate change is going to be reducing the mean trophic level of the system as well. So there are two simultaneous threats occurring in the system. What's interesting is that if you look at the Azores and Saint Helena, as my kind of gut reaction was going to be, my expectation, was that those dots of the unexploited system are at the right-hand side of the Pareto front. So you get your highest mean trophic level by leaving the system alone. For the Celtic Sea, the Norwegian Basin, and Senegal, actually, the cloud of simulations from the fishing practice has pushed us into larger values to the mean trophic level than leaving the system alone and unexploited. So that requires a little bit of explanation. It suggests that we're able to manage the system to increase mean trophic level. And given that those Pareto fronts are overlapping on the x-axis, it's also possible for us to manage the system of our fishing in order to offset some of those climate impacts on the food web. So what we can do is we can filter out the simulations. We can try and take just the top 5% of values in terms of mean trophic level and see what those simulations, what those management strategy possibilities have in common. These are the different relative fishing efforts across the 10 harvestable gills in the model. And what you'll notice is that the benthos and suspension deposit feeders on the second column are all in agreement that those need to have a high relative fishing effort to achieve a high mean trophic level. The same is true for harvesting macrophytes, and we've got an agreement on the low relative fishing effort for the migratory fish. All the other harvest ratios have got a rather large spread attached to them, so that means there's actually free choice. You can achieve your top 5% of the mean trophic level values by having a variety of different options for those other harvest ratios, those other fishing efforts, provided you harvest your benthos and you harvest the macroalgae. So who wants to eat a plate of seaweed and barnacles for the next 50 years? That's the question. We can come back to our cherries, just to wrap up, and say that are these the right things that we want to be doing? That's the set of strategies that satisfy those metrics, but are they the right ones? Mean trophic level is actually going up here because we're mining out the lower trophic levels. It doesn't mean we're making the rest of the system healthier. So you get a bigger number by taking out the low values in that average. Maybe we want to instead be focusing on actually making the system better and being more specific about the biomasses that we are wanting to encourage. Similarly, for the human appropriated net primary production, maybe we actually prefer certain forms of that primary production. Maybe I don't want to eat barnacles as much as I want to eat fish. So again, if we're more specific on the metrics we want to be using and what these objectives are, we'll be able to filter out these better possibilities. But ultimately, we need to be clear on our aims to be able to filter out the best strategies. So with those few questions going back, I'll now pass it back to all of you and say thank you very much.
Thank you, Jack. Are there any questions? Yes, there's one question here.
Yes, thanks. In your kind of a Pareto plot and frontiers, all the inner points are kind of points that are possible solutions of the problem.
I wouldn't describe necessarily solutions to the problem. They're possible combinations of fishing effort you could choose.
Yeah, so possible configuration of.
And a lot of them I wouldn't advise choosing because you can either increase the amount of fishing you're doing and not affect the kinship level, or vice versa.
So you will converge towards the frontiers of that point. But my question is about, does it say anything about the resilience of the system?
Not in of itself, no. I mean, there are people that have been investigating the linkages between different metrics of network structure and how that translates into resilience in the time, but this is all about steady state. This isn't about looking at transient dynamics and time to recovery from perturbation. So we need to do some different simulations for that.
Okay.
We are behind schedule, so I'm afraid we don't have time for more questions.